go to what we left off last time. Last time we were talking about an algorithm, how to compute maximum independent set, right? And we came up with a recursive algorithm, like divide and conquer algorithm, whose running time looks like this. Okay, this looks like some recursion that recurrence that we haven't seen before, and I claim that it just solved to this one. Like if it was like if it looks like this, poly n, then this is kind of easy to solve because you can observe that like you can kind of unfold this thing n times, right? Like you're gonna kind of just keep unfolding this, and you're gonna do it this kind of n times because each time you reduce n by 1, each time you like incur a factor of 2, so you get something like 2 to the n. This is kind of easy to see, like and not too hard to like kind of at least intuitively guess what's the right bound. But what about this one? How can you solve this? So today I'm just gonna tell you like a formula how to solve this, and also tell you an intuitive way why it should like this method should be true. But like the formal proof, you can look it up. Yeah. I give the resource though that you can look it up. So let's see why this is the case, right? And the method that like how did I do it? Let me at least tell you like in step what I did. Like given this recurrent, right? So I kind of I just look at this formula. So it's like you kind of write it down like this is maybe I go to this method. No, yeah. If you have any formula like this, right? You have Tn equals some polynomial factor plus like some term like of the sum of t of n minus ai, and there can be many terms, right? So what you do is like you take, let's say b is the maximum of ai, then you look at the polynomial x to the b minus this one. Okay, so what it is for us, like a b here is 2, so I just write like write a polynomial x to the b and then minus here, which is like x to the b minus 1 and x to the b minus 2, and this is a polynomial that I look at, which is x minus x squared minus x minus 1. This is my polynomial. Okay, and then I ask what is the largest root of this polynomial. Like let r be the largest root of this polynomial. So basically I ask what is the largest r such that this is true. Okay, so the largest r that this is true is just well like is something like a golden ratio, which is 0.618 something like this. So okay, then the theorem just said that okay, if once you know the largest root, then you just say that like t to the n is at most r to the n. So which means that like this guy is just at most this thing to the n, which is at most like I can get the worst estimate, which is 1.62 to the n. Okay, so that's that's the method. Okay, why this works at all? Okay, at least, but any question about like the method first, not about why it works? Okay, good. So now let me tell you like why this should be true. Okay, if you want to see like a formal proof, you can look at this lecture note. It's some like kind of algebraic proof, but I want to tell you like at least my intuition, like why this work at all. Okay, so the intuition is this: when you have this kind of recurrent, for example like this, you can guess that like the right answer is going to be some exponential bound. First of all, because like the way that this thing reduce its size, it just reduce its size by like a constant. So like the tree depth is kind of order of n, not order of log n anymore. And like if that the tree depth is order of n, then like each time you kind of multiply the size of the total size of the subproblem by like some constant factor, and there are an order of n level. So like it's like 2 times 2 times 2 times 2 n times, or like some other numbers. So that's first thing is like this thing looks like a exponential bound. Okay, so now once you know like that this should be exponential bound, the only thing you need to ask yourself is like, okay, this should look like something like r to the n, and now what is r? What is r? That's the only thing you need to ask. Okay, so let's try to like prove like try to do something by induction. Okay, I don't know yet what r is, but I gonna say that this thing looks like exponential. So let's try to prove something by induction. That is, let me do this for this example. I guess now that t of n looks like r to the n, so I can just write down that by induction, this thing is at most poly n plus t of n minus 1. So by induction, it's gonna be r to the n minus 1, right? Plus r to the n minus 2. Okay. And how to complete my induction? I need to prove that this whole thing is at most what? To complete the induction, I need to prove that this is at most r to the n. Like we want that this is at most r to the n. If I can choose r such that this is true, then this would complete the induction. With me? Okay. So now we can just ask, okay, what is a r such that this is true for sure? So, well, like then, like how to say this is just okay. Poly n is kind of negligible compared to the exponential bound. So you can just ask like, okay, what is r such that this thing plus this thing is at most this thing, and then to find this you can factor out like it's just you can factor out r minus n, r to the 2 n minus 2, and you get this thing. So I cancel this thing, right? So this is basically if and only if R. Okay. So you can see that we kind of get like the same polynomial here. And okay, we ask like, okay, what is the R such that you know for sure that this is going to be at least 0? So you just need to take something such that it's larger than the largest root of the polynomial. Like if you look at how to choose R, this is what we want. Choose R such that this is true, then just such that this is true. Then how to do this? Just choose R such that it's larger, such that R is larger than the largest root of this guy, of this polynomial, right? Because this polynomial kind of looks like I don't know, something like this, like it's degree 2, so it looks like something like this. And if you choose something that is larger than the largest root, then it's going to be more than 0. Yeah. So you say like we just try to choose R such that you can complete the induction step, and like just choose the best R such that this is true. That's how we did it. And in general, like when the recurrence look different, you're gonna end up with like a different polynomial, but basically it's the same idea that I just argue. Questions? Okay, good. So in your homework, you need to solve one of this type of recurrent, yeah. And you can just use this method. You don't need to prove it. Okay. So that's it about divide and conquer. And we're gonna proceed to the next part of the course, which like for this week, it's gonna be about dynamic programming. And just to remind you that problem set 1 is due in a week, and the concept will go through everything before this. Yeah. Okay. And for this week, what we're gonna do is like look at dynamic programming. Some of you have learned about this in 376. But what we're gonna do is like you're gonna see many more examples that is more advanced of dynamic programming. But I will start with this thing that you might have learned. The first example that we will learn about, you might have learned it, but I want to like start with the basic one. Okay. So this is the most basic problem to use dynamic programming, and let me tell you what the problem is again. Like the problem is like you are given like a set of jobs. Each job looks like an interval, like this, right? So it starts with like each job is an interval where you have the start time, the finish time. So this is SI, and this is FI, finish time. And it also has the value of VI. Okay. And what we want to do is that we want to like find a subset of compatible jobs or intervals such that they are disjoint. Like subset of job, I said that they are compatible if the intersection of interval are empty. That is, they are disjoint. Like this pink one, they don't overlap. If so, then I say it's compatible. We want this kind of set of jobs. Okay.
What does VI represent?
It's a number. Yeah. It's like a value of each job.
How important it is?
How important it is. And yeah, so the goal is just to return like a compatible subset of jobs, such that you maximize the total value. So you can think of this as like the class that you can take, and you want and the value is like how much you like it, and you want to take like a disjoint set of class that don't overlap, don't conflict, such that you maximize your welfare or something. Yeah. Okay. So that's the problem. We want to solve this. Okay. And now, okay. And by the way, I'm gonna assume that the job J1 up to Jn is ordered by its finish time. Okay. So if we want to solve this, the idea is the following. Let's try to consider the last job, the job that is ending last. In the in the optimal solution, you have two options: whether this last job is in your solution, or it is in. It's not in, or it's in. Okay. Okay. So let's try to guess like what is the correct answer. So suppose that the last job here, Jn. Suppose that it's not in the optimal solution. So if you reject this job, then you know that if you know that this last job is not in the optimal solution, then the optimal value of how to select this subset of this set of job is just the same as how to select everything except the last job. The best way to select everything except the last one. Okay. So suppose that you know Jn is not in the optimal solution, then you know that this is true. But what if you actually know that Jn is in the optimal solution? Then you will put this into your optimal solution. So the optimal value here is going to be at least Vn plus something here. What's going to be something here? Well, if Jn is in your optimal solution, then anything that overlap with Jn, which is this guy and this guy, you know that they cannot be in your solution, right? So let's say that let me say that I is the index of the last job that is disjoint from Jn, that doesn't overlap with Jn. So it's going to be like this one, for example. Okay. Like I here is going to be n minus 3. So because Jn minus 3 doesn't overlap with Jn. Okay. So then once you know that this guy cannot be in the solution anymore, the optimal solution will just look like Vn, like the optimal value is going to be just Vn plus the optimal value of every job up to this guy. Okay. So question about these two equations. Okay. So we have now we have basically a recursive algorithm, right? Can you tell me with these two equations how would you come up with a recursive algorithm?
You would just consider the maximum of the reject and the acceptance.
Exactly. Yeah. Just like, okay, you have a problem with like n jobs. Now just try both case and return the maximum. How to compute this thing? Just compute recursively. Okay, so that's the recursive algorithm, and you can just write it down in pseudocode like this. Okay, just take the max of the two cases here. Okay, all right, but like if you just solve the problem in this way, then the recurrent maybe look like t of n plus 2t of n minus 1 plus on, right? Because on here is just to compute I, and each of these, like the size of the recursion is of size at most n minus 1. And this is not great, right? Because we know that, okay, when you have this recurrent, it gives you 2 to the n. Because the depth of the tree is like n, and in each time, you kind of create like 2 more subproblem. So yeah, the total number of subproblem at the end after, like at the depth d, there will be 2 to the n many subproblem, and the depth is n, so it's 2 to the n. That's not good. Okay, but we don't really need to spend 2 to the n time. And there is one key insight, like this seems really bad, but there's something really like not efficient about this algorithm. Can you tell me what it is?
The subproblems are overlapping, so we only need to do t of like n and t of n minus 1 once each, and then we can just access problem minimalization.
Very good. Like, so many of these subproblems, they are actually looks like the same subproblem. They overlap, or even they are the same sometimes. So you are kind of, the way to recurse like this is just recompute the same thing again and again and again. Not good, right? And to make this formal, you can see that the kind of recursion that we do, if you have n jobs, the format of the subproblem that you look at is going to be always like a prefix of the job that you have before. Okay, so if you have n jobs, j1 up to jn, you're gonna recurse on like a prefix of your jobs. So j1 up to some ji. That's the type of subproblem that you ever look at. And how many prefixes are there when the set is of size n? It's just n many prefixes. So although these three have 2 to the n nodes, there are really like n distinct subproblems among these 2 to the n nodes. Okay, so most of these guys are the same. Okay, so, and if they are the same, we don't want to recompute. And how to avoid recomputation? Well, you can just remember what you have computed before, right? So that's the idea. If some kind of this subproblem are the same like of this one, if you have computed this subtree before, when you wanna compute this guy, you don't need to recurse and everything, just return the same value that this guy have been computed. Okay. So with this idea, you can just write down almost the same recursive algorithm, except that now you have like let's call it memo for a table lookup table, right? And memo is an array of size n where memo k will store like the optimal value when the input is like j1 up to jk. Okay. And now what we're gonna do is, okay, whenever like if you call like a sub if you call the problem on this um, this on this set of jobs, you just first check if you have already computed something or not. Like check if like you initialize memo by like a question mark. But if you have computed something already, just return what you have computed. And the rest is just the same recursive algorithm. Otherwise, if you didn't compute it before, then just do the same recursive algorithm. And if once you know the answer, remember what you compute in the memo. Okay, which means that if you ever need to get this value again, you don't need to recurse. You just return it from here. Yeah.
What is the index of memo? How are you able to look something up? Just curious.
Memo is like an array.
Yeah.
So like an array of size n where each entry is store a number.
How do you know which one to look up though? I'm just wondering.
Oh, so if this is like if there are like if the input is of size n, you then look up memo at location n.
There won't be any like duplicates or anything.
What do you mean?
So there won't be any like duplicates where you have two different solutions, I guess.
Well, so memo k here, right? Memo k just store the optimal solution when the input is this one. So there are only one number that is assigned to memo k. There is no duplication. The idea is just like the type of input, like the possible inputs, there are like just n many possible inputs that you ever wanna look at. So for those n inputs, there are n outputs, and each of the outputs you just store in the memo. Make sense?
Yeah.
Okay. All right. So that's good. Now I'm gonna skip the running time analysis for a bit because the next version is easier. But this is called top-down dynamic programming because it's still a recursive algorithm. It's kind of called from the top and recurse down, right? The difference from like a normal recursive algorithm is that we have memory. We store, like it's called memoization. We memorize what we have computed. And like if you, it kind of look like try to reuse a tree node whenever possible. So hence the picture here. Anyway, there is like an equivalent way to solve this problem. Okay, so we were trying to solve the problem by like writing down a recursive algorithm. Now, but what we know is that there are n many subproblems we ever gonna look at. So what if we just try to like compute this, the value of this n subproblem bottom up instead? Okay. So what I'm gonna do is instead like okay, define memo in the same way. It should like a memo k should store like the optimal value when the input is j1 up to like memo I, so the optimal value when this is j1 up to ji. Okay. I assign like a memo of 0 to be 0 because the best case is there's no job list. And now I'm just gonna try to compute the value of memo on every value. And I can just do it from 1 up to n. I don't do it recursively anymore, I just do it bottom up, right? So start from 1, from k equals 1 up to n. Just compute the recurse, like this is kind of the same the same recursive formula we have before, but we just like that is like we compute I. This is like the job that is before k and doesn't overlap with k. And what's the optimal value of what's the value of memo k? This is just the same recursive formula, but observe that I know actually that I don't need to recurse, because whatever I want to compute, like whatever I need, I have computed before. This is I want memo of k-1. It must be computed from the last iteration already. I don't need any recursion. And this one is just some I is less than k. So I have computed also as well. So just no recursion, really. Because everything that we ever need, we make sure that we have computed before. Okay. So question about this different implementation of the same idea. Good. So now with this kind of different implementation, it's kind of easy to analyze the running time, right? Because, okay, to compute I, you can do it trivially just by scanning through all the jobs before k, check which one doesn't overlap with k. That takes O(n) time. And there are n rounds of loop. So that gives you now n square operations. It's not exponential anymore. Okay. So this kind of exponential improvement is something that is really fantastic about dynamic programming. Like you can improve from exponential to polynomial bound. Okay. Now just a few words about the two implementations. We just look at the bottom-up one before, which is the one that just compute all value of subproblem that you ever need, bottom-up. And top-down one is just the one that kind of try to compute the value of subproblem that you need. Okay. So in principle, like the top-down one should be faster, because it's like you try to compute only the thing that you really need, and you still compute each subproblem like once. The bottom-up one just compute everything from scratch. But like this is something that I'm not sure in practice. It could be that bottom-up is faster because kind of you don't like when you implement a recursive algorithm, like maybe the memories go everywhere, like kind of in many random places. But when you do bottom-up, like you might have like exploit cache in, I don't know. But the point is like, but if you care only about the theory, this one is definitely easier to analyze, right? The bottom-up one is just kind of more straightforward to analyze. But top-down should be faster in theory, and in practice maybe too. But I wonder if maybe the cache is not like you cannot exploit cache as well as in bottom-up. So I'm not sure. Yeah. By the way, like just for this problem, I claim that like this operation you can improve, like to find the I that doesn't overlap with k. You can do it faster instead of n time. You can do it in log n time. Anyone have ideas how?
Maybe you could make another array that has start times in it, and then like find the indexes will all align between the three arrays, and you can just find the right start time.
Good. Like, well, it's like you have an array that store like the sorted array of finish time, and now you have the JK. You know the start time of JK, so you can just like start time. Okay, you have start time of K, and you have array. This array of like a finish time. J up to Jn, right? So you just need like the one such that like the biggest finish time that is smaller than sk, and this you can do it by binary search. So that takes log n. Okay, so pre-process this one. Like store this array, and now you can look up for I in log n time. So the total time is going to be n log n instead. All right. Okay, this is just like the first example that you might have seen for dynamic programming. But like I want to compare dynamic programming and divide and conquer. What they have the same kind of thinking that you need in both paradigm is that you're given a problem, you just try to split the problem into sub-problems. They are the same type of thinking. However, like for divide and conquer, you don't try to remember anything, because there might be like too many possible sub-problems that you cannot just try to compute everything and prepare everything, but instead you just try to make sure that the size of your sub-problem is small and the total number of sub-problems that you recurse is not too many. So you try to get the best recurrence basically, and give the good bound from your recurrent. But for dynamic programming, this will be super effective. Well, when you observe that the total number of subproblems that you ever encounter is actually not too many. Once you observe this, then you know that what you can do is just to save all the answers that you ever need and do it bottom up, and you don't need to recompute like the same subproblem again and again. Okay. So again, to design dynamic programming algorithm, you try to write down recursive formulation just like divide and conquer. But then this is the important thing. See first whether like the number of subproblems that is possible is small. If so, then just create a table and try to fill in bottom up. Okay. So that's kind of abstract. So let's see more example. We're gonna just keep seeing more and more example. Okay. All right. So the next question that we gonna look at is edit distance problem. So suppose somebody type a word like a Thai Lund. So you need to suggest the correct word. Like it should be maybe Thailand. Yeah. So that's what we want, and let's try to model this problem into like some computational problem. So it's called edit distance problem. So maybe like suppose that you actually want Thailand. So you ask like what is the total cost of edit operation from this word to this word? Okay. Like from some word that is given to you to some word that is in the dictionary. Okay. And like you want to maybe find like the one that is smallest, like the most correct one. But at least you need to know like what's the distance between this to this, and that's our problem. So it's like you are given 20 two string A and B, okay? And you ask for the total cost to transform A and B to B. And let's say that maybe the cost of inserting a character is CI, the cost for deleting a character is CD, and the cost for swapping some character to another is CS. Okay? So suppose that each operation have different costs.
Are all like swaps are all swaps weighted the same? Because like intuitively I think like swapping like a vowel for a vowel should cost less than swapping a vowel for not vowel for this. Is it all the same?
For this, let's say they are the same, but you're gonna see that like we can generalize this to something else quite easily. Yeah. To handle like for vowel to vowel, it should be have different costs that you can do. Yeah. Okay. But yeah, like you can try to like come up with something different here. Yeah. But for this class, let's say there are just two type of costs. Okay. So that's the edit distance. You want to minimize the cost for this edit from A to B. Okay. And let me mention another thing called string alignment. So edit distance is just a number, right? But what we want is string alignment, like that is try to tell you the best way to transform A to B, like not just a number. What's the cost? Okay, so what's string alignment problem? So it's like we have maybe thing like this. You have A and B, two string, okay, and basically the task is to insert a blank character to string A and B, such that it minimizes the cost, where the cost is like this. If is like a blank in A to anything in B, like here, this is like to insert E into A, right? So this is like you pay CI, and you insert this to D, like you insert D, you insert I, okay? And if you want to change any character in A to blank in B, then this is like a deletion. You pay this, you pay CD. CD, this you pay CI. Okay. And to swap, then you pay CS. And if they are the same, then you don't pay anything. Okay. So we kind of what we want is to find like to align the two strings by inserting this blank and so on. And for each fixed alignment, then there's going to be a cost associated with it. And if we can find the best alignment, then we know edit distance. We know the best cost. So in this case, you have that, like if you can align in this way, fix this alignment, then the distance is at most this one, like 3 insertion, 2 deletion, and 4 swaps. There might be a better way. We want to know the best way. Okay, that's what we want. We want the best alignment so that we can get the best, like what to compute edit distance. Okay. Question about the problems? Okay. By the way, this problem is really like useful in bioinformatics, and this is a software that solves something similar to edit distance, but they like really engineer it really nicely, like, and it's used really a lot. But for us, let's look at the basic question, like this basic version. Okay. Right. How do we solve edit distance? If we want to try dynamic programming, the first thing we want to do is just try to think of recursion. That's the best. That's the first thing. If you want to try dynamic programming, try recursive strategy. What should be a recursive strategy here? Then, okay, how can we, if we have a distance problem, how can we recurse? So the first idea might be, let's look at the last character of two string. Okay, and you can just ask like, how do we want to align the last two string, the last two character? There are really kind of not too many options when you just look at the last character of the two. Okay. Well, the option one is like we're gonna say that I'm just gonna like delete. I'm gonna delete L to blank. In this case, I'm gonna play the CD and I'm gonna recurse on the whole word of B and everything in A except I delete L. The second option is to insert. I'm gonna insert from blank in A to the last character in B. So I'm just gonna like align blank to E, right? In this case, I pay insertion, one insertion, and I recurse on the whole A and like everything in B except the last character. The third option is just swap from last of A to last of B. You pay one swap, and now the size of A and B are now decrement by 1. So once you see that, like there are just like not too many options. In this case, 3. Actually, there are one more option. What I'm missing?
Is it swap?
Swap is here.
Not do anything if the characters match.
Yeah, I might not pay anything actually if the last two characters match. But in this case, they are not the same, so I have 3 options. If the last two characters match, then I would kind of look at this option and pay 0 and recurse on A and B where like the size of A and B decreased by 1. Okay. But now you get like a recursive formulation. And once you have a recursion, you have a good starting point for dynamic programming algorithm. Okay. Any question about like why this recursive formulation is good? Right. Okay. So with this, you can write down recursive formula, which is like a distance from A to B. It's just like, okay, just try, there are 3 options. Just try the best of the 3. Like to delete or to insert the last character or to swap or match. Right? We pay like 1 swap if they are not the same, else 0, and then recurse on A star and B star where A star and B star are just A and B when you remove the last character. Okay, good. So we have this recursive formulation. That's the first step of dynamic programming. The next thing is just you need to think how many subproblems can there be in this strategy. Okay. So anyone want to answer me? Yeah.
Is it like length of A times length of B?
Yes. Why is that?
Because you have to consider like every
Prefix.
prefix of A with every prefix of B.
Exactly. Good. yeah, like the type of subproblem that we look at, we recurse only on some prefix of A and some prefix of B. And then that's why like they are just, this is a type of problem. So like there are like a many prefix of A and B many prefix of B. So there are this many subproblem. A times B. Okay. Once you know that the total number of subproblems you ever encounter is polynomial, kind of have a good chance like that you are almost done. Just try to fill in the table so that you know all the value of this subproblem. Okay, so you start with the table. Okay, and a table like should look like this, where this part is just like a kind of distance from two empty string, and I put it to be 0. And this thing should be like distance from this prefix to this prefix. And what we want is just the last guy here. This is what we want. We want to know the best way to transform A to B, the whole A to the whole B. So this is the number that we want. Okay. All right. So now we have like we can imagine the table, and now let's try to just fill in the table. So just create a table like this, memo, which is a 2D array. Okay, like I just drew last time, like before, and we're gonna like kind of write down like the best case here. The memo like here, memo j to 0. Memo j0 is just the distance like from prefix, the j prefix of A to empty string. That is like you just need to delete everything j times. So that's why it's like this. And this is just the distance from empty string to the case prefix of B. So you just need to insert k time. So that's like just kind of the first row and the column, the first row and column here. That's the our base case. And now, what about this part? The remaining, how can we fill in this? Just use our recursive formulation, and that's it. We are done. Okay. So there are like A times B rounds, and in each round you spend constant time, because whenever you want to compute a number in the table, just compare these three numbers. Each of the number you have computed before, nothing to do, no recursion. So that takes order of 1 operation. So the total time is just A times B. That's the total time. So let's try to fill in the table. Like let's say that like all type of C is like 1, like CI, CD, CS is 1. Then like you need to fill in this, right? So what you need to do is like you kind of take this one, the minimum of these two, like, and you're gonna get 1, because like this 1 is gonna be plus 1 here, and this plus 1 here, but this is 0, and you just pay 1. So you kind of you get 1 here. And for what about this one? Well, you're gonna actually, yeah. Can you tell me what should be the value of this one? Just to check your understanding.
Is it 1?
Why? It's correct, but why? Yeah.
There's no change needed.
No change needed. So yeah, like there's no change needed. So this guy meshed together. So you can kind of recurse to here, and you pay 0. Like you take the value here and plus 0. Yeah. So it's basically this case, but plus 0. Okay. And you fill everything in, and now you get edit distance. Okay. And so now we're kind of done. I want to mention one thing, like a nice way to think about this is actually that the distance is gonna be the same as the distance in the following graph, where it's just a graph where you kind of almost like a grid graph like this, and here is just like the operation where you pay CI. Here's like you pay CD, and here you either pay CS or 0, depending on whether like the character here and here mesh or not. Okay. And so what you want is basically the distance from this node 0, 0 to this node in this weighted graph. The distance is just exactly the same as distance from this node to this node in the weighted graph, in this weighted graph, if you think about it. And now if I ask you, okay, edit distance is just a number, but at the end of the day we want the best alignment. Remember, like how to align to string, not just the cost. How can we get alignment? Not just a number here.
Just to go to one of the 3 points adjacent.
Say it again.
Like there's like 3 points which are pointing to it.
Yeah.
With only one maneuver, so you have to get to one of those 3 first.
Yeah, like so you said that when you are here, there is the best way to come to this point, either from here or here or here. And when like if this is the best way to come here, then you know that like you should align by like a swapping or mesh. If the best way is to come from here, then you know that you need to delete. And here you need to insert. Another way to set it is just you can just take, let's say this is the shortest path. If this is the shortest path, then basically the shortest path just tells you exactly what's alignment. Because the shortest path just say like, okay, delete, insert, delete, mesh, or swap, and insert, and so on, right? So just by looking at the shortest path in this graph, you're done. Good. Question about this problem? So we conclude that we get the algorithm of running time A times B. This is quite a simple problem, and you might ask, can you improve this at all? Like, you might wonder, can we improve this running time of A times B? And it turns out that like people have tried really, really hard, by the way, to improve this, and that's the point of this software blast for bioinformatics. They have so many engineering tricks to improve this, but it turns out that in the worst case, the answer is no. If you assume something called strong exponential time hypothesis, is something about like a conjecture that you cannot solve set in times better than 2 to the n time. I will not go into this. I just want to point you out that there is this area of in TCS called fine-grained complexity. Okay. Let's try to argue something about this, like that you cannot even improve some running time by like a tiny factor, because if you can improve it, then it will contradict some conjecture. This is a pretty cool area of research, and like there are Nicole Wine and me. We are doing research in this area. If you want to know more, you can talk to her or me. Okay. All right. So what I want to say is just assuming this some conjecture, this simple algorithm actually is the optimal one. Okay. So, okay. All right. Let's move on to the next one. So the next example is called multiple matrix multiplication. Okay. So in this problem, you have list of matrices. Like A1 is like some matrix here. A2 is like maybe another matrix, which is maybe like this size, and next guy maybe it's the matrix of this size. Okay. So it must be that like AI is of size AI is of size Ni times Ni plus 1. Okay. So, and we want to compute this product. Okay. You have a bunch of matrices. You want to just multiply them together. That's what we want to do. And if you have two matrices of size, let's say M times P and P times, let's say P times N, you're going to multiply them and get this matrix. And the cost for multiplying like matrix A and B to get A times B, like the cost for multiplying this, at least a trivial algorithm, you're going to pay this much. Because there's going to be like a n many entries here, right, of this guy. And in each entry, you're going to need to multiply like this row with this column to get to this entry. So each entry you spend this time. There are faster way to do matrix multiplication, but let's say the cost is this. Okay. Right. And note that like matrix multiplication is associative. That is, if you want to multiply A, B, C, you can multiply this guy first and then this guy, or this guy first and then to this guy. However, the cost of like this choice might give you different costs. Okay. So let's see the example. If I have three matrices, like n by n, and n by 1 and 1 by n. Okay. So if I multiply A and B first, then the cost is n squared, and then I'm gonna get like a times B is gonna look like this vector. And if then I multiply this guy to C, that gives you another n squared factor, plus n squared. So the total cost of doing it this way is just order of n squared. But if I do it in another way, if I multiply B to C first. Then I'm gonna get like a matrix of this size n times n, and then multiply A to this guy. That's like you're gonna pay n cube. Question about this? Like that there are different way to multiply a sequence of matrices. Different way can give you different costs. Okay. So now what I want from what we want to do is actually given this sequence of matrices, we want to design what's the best way, which pair of matrices to multiply first, so that the total cost of getting our end result is the best. It's like is smallest. Okay. So I'm not asking you about what is the end result. I'm asking you about what's the best way to multiply this sequence of matrices. Okay. So given this sequence of matrices, output kind of the parenthesis structure that minimize the total runtime for multiplying. Okay. That's the question. And it's not that clear how do we approach this. But now let's try to let me tell you one first observation. That is, this problem is secretly a tree design problem. Because what we kind of want to do is okay, we ask what to multiply together first. Maybe I want to multiply this pair together first. And then maybe use this guy, multiply with this. Okay. And so on. Maybe next I say, okay, I'm gonna multiply these two together, and only after that I multiply these two and this guy to get this sequence, and at the end I multiply by A6. So this is kind of you try to design this binary tree such that the leaf are the matrices that you're given. Okay. Just by drawing kind of give you some feeling about the problem. And now, okay, if we want to solve this using dynamic programming, what's the first step? Come up with a recursive strategy. Okay, how can we try to get recursive algorithm from this kind of picture? Okay. Ideas? Yep.
Pick a pair and then compute the runtime of that, and then recurse on the smaller set of the remaining elements and the pair that you just.
What do you mean by a pair? Which pair?
Two matrices to multiply first.
Okay. So that's kind of bottom-up way to think about this. Maybe I ask what is the top-down way? Recursive is usually you think top-down, you might implement bottom-up, but how to think about this top-down?
You choose two ranges, so I guess you could, if I was one, that might be figure out the most you can get with A1 and A2 to A6, or A1 to A3 and A4 to A6. You just keep trying every range.
Yeah. So, good. So, to think about this top-down is you see that at the end of the day, we need to multiply everything together. And you just kind of ask where is a split here? So here is we have split of this guy and this guy, but you could have the split might looks A1 up to A3 and A4 up to A6. You might have this subtree and you combine it at the top. Okay, so the recursive way of thinking is just, okay, there are just n choice of splitting from the top, and whatever you need to do here, it's just the same problem on the smaller problem. Okay. So yeah, like here, like just need to decide where to make the top level split, and then recurse. Okay. And yeah, here like you split here and recurse on this guy and on this guy. So like the cost, for example, here, if I make a split here, is the cost on when I recurse on A1 up to A5 and just on A6. And then I need to pay the cost for multiplying this guy and this guy, which is gonna be like the dimension of this guy. And like from the dimension of this guy and this guy, I pay this much. Yeah.
What if the optimal solution involves like multiplying matrices that like aren't contiguous with each other in this like array? Like right now they're ordered 1 through 6, but what if you need to do like 1 and 6 together first?
Oh, so good point. Like actually, you cannot like for matrix multiplication you cannot do that because it doesn't commute.
Oh, right.
Like you cannot just say like maybe I want to multiply A and C first and multiply by B because that gives you might be different outcome. Yeah.
Okay.
Okay. So yeah, good question though. All right. So that's the recursive strategy. What's the next question? How many subproblems can there be? Can you tell me how many different subproblems will we ever encounter from this kind of recursion? Yeah.
Is it 2 to the power of n or?
It's less than that. Like here we recurse on this interval from 1 to 5. Here you can have recurse on interval of 3 to 5. Like the type of, so you can see that whenever we recurse, we can have recurse on something that looks like AI up to AJ.
Yeah.
Right? That's the format of our subproblem. It's just an interval start from some I to J. So how many subproblems are there?
There's n squared.
N squared.
There's only n squared possible matrices.
Yeah, like I and J can range from up to n. So that's like n squared many ways. Okay. So that's number of subproblems. N squared. Okay. And now you're almost done. Like we have that, okay. There are not too many subproblems we need to ever encounter. So now just try to fill in the table somehow. Okay. So just need to define what we store in each cell of the table and try to fill in that. Okay. So because the subproblem is like a kind of from I to J. It's like so it seems like there should be like a memo of I and J at index I and J to encode this thing. Okay. So I create a memo ij to store this guy. Right. And just need to try to define the best case, and the best case here is like, okay, if like okay, if this is like from remember at point I and I plus 1, actually sorry, this is like a kind of, instead of the matrix A itself, I just put down like the number, the dimension here, AI up to AJ, not the matrix itself. Okay, so if this is just like memo at I and I plus 1, then it's like I have one matrix of size Ni and Ni plus 1. Like it's just, so one matrix has 2 dimensions, which is Ni times Ni plus 1. So this is a case where actually there is only one matrix. I don't need to do anything. So the cost is 0. Okay. And then like for each, for like now that there are like some like entry I and j, I need to fill in this thing, and how to fill in this thing. Just try to use like our recursive formulation, that is just try all the split, like compare, like h is like where you split. The split is from I plus 1 to j minus 1, and once you choose this where to split, then you just kind of pay the first half and the second half, and you pay this one, and you just take the best split. Just take mean of everything, of all the choice here, and that's the cost. So this is just like the recursive formula that we just discussed. Choose the best split. Okay. All right. So that this thing takes On. There are n square many cells in the table, so the total time is n cubed. So this is almost done, except that there is something wrong with how we loop through the table. So I said it's wrong because actually it's not filling in the table in the correct direction. So let's try to see the table a bit. The table is like this. Like everything here, I don't even put, like, we don't need it, right? It's not feasible because I is more than j, and this is the best case of 0. And the way that I write down the loop here is that I'm gonna fill in it in this way. Okay. All right. However, if I try to like compute this guy, I actually need this, like this cell kind of need to know the information in this direction. So yeah, just 1 minute here. So what I should fill in table is actually fill it in this way. Like kind of try to fill it in this way, and in this way, and in this way. Okay. So now I just write down the loop in this way so that I fill it in the correct direction. And that's it. So what we get is like n cube algorithm, but actually there are faster way to do it. It's n log n, and you can have a look if you are interested. Okay, so good. So for knapsack, I'm gonna skip because it's in your previous class too, but if anyone never see it before, you can look at the slides. So that's what I want you to take from this class. this is kind of the key idea how to design dynamic programming. And next class we will see more example, harder one. Right. Okay, see you next class.